Okay, I'd like to discuss the theme of structural borne sound again. And this time I will investigate and share some experiments using a room acoustics software for the task. I'm using Odeon, a Danish ray tracing program. This is the latest version, and it's developed to do room acoustic calculations, volumes, large volumes, concert halls, or smaller rooms. You can even use it outdoors in more or less the same volume spaces. But here I use it sort of the other way around. Instead of filling the volume between walls and floors, I put the source inside the floor slab and let the floor slab and columns or slabs be the room for calculations. And this is an early attempt. This is my modeled room is a part of our office, and I have dropped sources here and measured the maximum levels at different positions. And this is another one where I measured the sound level across the here, and this is the simplest attempt. You see the source here. I use about the same sound level as we would record at 2-3 meters distance from a 40 kilo manual drop directly on concrete. And this is about 25 to 30 meters away, and the drop is about 1 decibel per meter, sort of. And the material is concrete, but the inside is a room, a low room, 20 centimeters or 19 centimeters of room. And the absorption is like concrete, and then I have used a low relative humidity of the air to simulate a bit higher losses, propagation losses at distance. And this is a second example. Here we have columns, which sort of acts like we have a shadow zone here, and they also act as small sinks in some way. Here we have, I thought it was a slab wall here, so the model is actually cut here, so you see what the level is with a cut in the slab here, and it's 85 ish, 10 decibel loss, and we get the reflections from the wall over, so you see a little bit traces here. And then we have another cut here and a cut here, and we see that we get shadow zones behind that. And here, far distance, we get about 75 decibels, which is quite close to what we measured. And then we see that we get shadow zones and some rays running over here a bit. Yeah. not really physical, this. But what should we say? It works pretty well for when you can see the source and the obstructions are fairly small. And the difference from the real situation with bending waves and different types of waves in concrete plate and columns and slabs, they will be dispersive in reality. In this model, we won't have dispersion. So all frequency components travel equally fast at the speed of sound in air. However, in concrete, the bending wave speed, 200 millimeter concrete, the bending wave speed is 100 hertz. Yes, almost the same as the speed of sound of air in around 100 to 200 hertz, I think, where we get the coincidence and more radiation. So that's a weakness, but one of the strengths is that you get reflections and you model a sort of a reverberation in the slab, which you do get. The room acoustics program calculates impulse responses from between 2 points, and in this case with the grid calculations you get example giving sound levels, and this is dBi maximum levels from a drop here. This is further development. Here I have added another floor and an extra set of columns. At this stage, 2 years ago, I think, the columns are open, and they are open to the openings in the slab, and you get sort of reasonable results regarding coverage, but the numbers are this is the floor below where we have the source, and this is the floor above, and the difference here is larger than what we measure, and it's about double as large in decibels. So the choice here with only one source and the openings doesn't work for propagation into a floor above or below. What's the refinement here? Well, I'm trying different degrees of reflections from transition order is the number of reflections, specular geometrical acoustics reflections you get before it the rays starts to behave more randomly, and it doesn't improve the situation. We see a little bug here in the program, and the model here is put together quite fast, and it's not perfect, so it might be the building of it that and here I do not really know what this, but I've tried different approaches, and I added a point source and then a surface source to see if it helped to feed some energy into all the slabs, and it didn't really turn out well. And the calculations take quite a long time. I used a higher resolution and tried to feed many rays into the system, and it's about 8,500 of those grid points, so it takes days. And but here it took a long day for the calculations with two sources, a plain source and a single source. Now, this was 2 years ago. I've been looking a bit further into this summer, using a spreadsheet and a simple transport function, and I ran into problems with the it's very tedious, takes a long time, and so I wanted to see if we could brush up this room acoustics model and see if we can solve the problem with the transport to the next floor. And one of the fine things you can do with Odeon is you can trace the rays before you do the calculations. And here we will see, here's a source, you see the columns, you see the lights in the floor there, and we can let it free run, and it will show I think it's the first 10 or 100 rays all the way to the end, and we see that the ray bounces up and down very many times when it travels through the slab there, which is probably a property of the source itself. In a room, that is a good solution. In a plate like this, it probably is should have been better with a flatter distribution of rays. And I've tried it. You can put on a directivity rows, and I made one flat one, but it didn't seem to improve the situation really. It just seemed to work with the energy going. The rays will behave like this anyway. We see that there are rays into the some of the columns. There are only one ray entering the floor above, which is insufficient. It will also probably reflect the fact that there is less energy going up, but not as low as we see here. Now, when we move the source into the column, take another column, one further away or closer to the there, then we're closer to the main source, and then we try again. We get more distribution into both floors, and we see the same tendency that the reflections, it's a lot of reflections up and down, not really physical for waves traveling in a slab or plate, but it is a distribution of energy, and that's what we are after. And I've also tried this with a model with slabs instead of columns, and then it actually works with only one source in the lower floor and just the openings through the slabs to the next floor. But for the columns, the area is too small in relation to how the program works related to the ray density. So we're stretching the program beyond what it's made for, really. So we have to experiment a little bit to make it work. And the solution for the columns has been to add some energy at the top of each column related to how much structural borne noise there are around the column, and then I've done calculations, and you get reasonable results, more reasonable results. And this is a solution with the sources up there, and you see now we have a difference between the floors that are almost what we measure. But when we look at the decay of energy through the floors, I think it's not this was for slabs. This is for also slabs. One with the columns, and you see here the blue ones here are the grid points, sound levels, dBA levels, in relation to the distance from the source. The blue ones is the first floor, and the brownish ones here are the upper floor. And we see close to the source, this is 5 meters from the source or so, it's about 10 to 13 decibel difference. But the sound levels seem to drop slower in the second floor than the first floor, and I'm not sure if that is correct. And then we get the shadows zone data here, probably not physical, and the reason for that is that I haven't bothered to, or the reason is simply that it doesn't work around corners when it's a large distance from the source, I guess, or maybe it's a bite as this, I don't know. I only have measurements up to about 30 meters from the source, but I know we can still hear a drop so there will be signals further on. Now I have more. Yeah, this is the levels at each column, and further on I haven't bothered to fill the full floors there, and here is an experiment with a source inside a column, and then you get more reasonable data in both floors. So as soon as the source do send enough rays into the second floor, it will work pretty much okay, I think, but it's not physical to do so. It's just tells us that we can work in ways like that. This is one source down here, and openings in the slabs, and I look at the distribution in the first floor here, and we see that there will be stronger response in the central part here where there's no slabs. I don't know if that is physically correct, but we'll figure out. Yeah, I might have fixed. Yes, here I experiment with, because you can put on sound insulation in the I don't know, this. Yeah, I have one here. This is transmission, and this there's a brick wall there, so I've modeled that with a transmission, and it's 3 decibels loss there in the model. And actually we could, if we wanted, we could have modeled both the sound going in this structure and entering the rooms, but I haven't gotten there yet. But there are, you can put sound insulation properties on the walls and surfaces, but I will have to build the model a different way to do that. You have to have separate pieces for walls and so on, and that's another step. Still, we see here is a cut. Nice to know if you deal with floating floors and you don't have cuts all around. What did I do here? Not sure. I haven't put, there is 0 transmission loss here. Maybe I've opened up it was the transmission loss there. Well, it's still there probably. Well, it's a lot of information, and here I've put on transmission loss on its 2 sides for every slab, and then the number of rays becomes too low, because adding a transmission loss also makes the 3 decibels transmission loss reduces the ray numbers to half, I think, because that is possibly the situation they model the loss of energy. I don't know, but I think so. So we have problems here again, and there is junction losses at between walls and slabs and floors like this, also for the columns. So it's a more realistic situation to add that. Here is a version with where I have put the sources on top, one source on top of each slab, and I'm getting a better representation again in the second floor. And this is the column situation. So and we see in the lower floor there is, if you do add junction losses, you also get a more realistic situation regarding the vibration level in the floors beyond the slab, I think. But we will have to do more measurements points and so on to confirm this, or to learn more. Also need to learn more about what the correct transmission loss is here, And the really interesting question is what we do to the next floor. Of course, we will have to add energy, but the results will probably depend quite much on the choices we have regarding those sources. And one of the problems with the calculations and so many grid points as here could have been done well with half of them, but still the calculations takes a long time, 5 days for this, and the calculation time will, I think it will add up for every extra source you have running at the same time. You will the time will go up. In this case, I think it's 15 times what it will be with only one source. So, and I haven't. I would like to try line sources, but I think maybe it's faster. I don't know, but it's safer to use point sources because the industry bit of the program with surface sources and line sources is coarser, sort of, than what you need for a concert hall. So the points are safer sources, I think. For these calculations, I actually use the same numbers as for the columns. So I should probably have changed the energy, the correction for each of these a bit better. Yeah, I think that will be all for now. I think it does have potential. The method does have potential. But you need to know quite a bit about, for instance, sound insulation calculations or impact noise calculations between rooms, and the properties of junctions, and how you translate that to something you can use in this program. Moreover, you need to know quite a bit about the source, which is one of my strengths. I know what you can expect and what drop energy and sound levels you will get. I know what the answer is, at least for the same floor. And it's quite easy to test when there's not many people in the building, and also the transmission loss from the floor below to the floor above is quite simple to measure. But you need to know the instrumentation. I use an accelerometer, but you can do it also with a sound level meter if you can have closed room for those. Yeah. So if somebody will pick this up, it might take 2 years until next time I will have time to look into this, or 1 year, I don't know. It's easy in the summer holiday, not so easy during work season. I'm not sure if we get a project where we can develop this either. So if anyone will pick up on the idea and try and maybe share some ideas and experiences, that would be great. So thank you for now.